Welcome back. So, as we saw earlier, MobileNetV1 is extremely fast and efficient. It's accurate. However, authors have expected that some users of this model may probably want to make it even faster and smaller. Therefore, they have introduced two hyperparameters for such purpose. They are called shrinking hyperparameters. So this is what I'm going to do in this video. I will talk about these shrinking hyperparameters, and afterwards I will mention some of the key results that attracted my attention in the experiment section. So the first thing I would do is to talk about model shrinking hyperparameters. Shrinking hyperparameters. So there are three techniques, but for the shrinking hyperparameters there are only two. So the first is called the width multiplier. And it's denoted in the original paper as alpha. So basically what this does is it reduces the number of kernels used in the convolutional layers, and when this number of kernels is reduced, then the depth of the output is also reduced. So alpha ranges from 0 to 1. When alpha is equal to 1, we have no shrinking at all, so the model is the same. In this case we talk about baseline. It's called baseline MobileNet version 1. Otherwise, if alpha is smaller than 1, and of course should be higher than 0, then in this case the width of the activations, or rather the depth of the activations, would be reduced because the number of kernels would also be reduced, right? So for example, let's consider the following situation. If you have an activation like this, and let's say that the dimensions of this is say 112, 112 and 64. So this is for alpha equal 1. If you have an alpha that is equal to 0.5, then this would be multiplied by 0.5 and you'd get 32, and we get such shrinking in the depth because the number of kernels is reduced. So now, what is the computational cost? So first of all, let me remind you of the previous computational cost of the MobileNetV1. So this was x1 equal dk times dk times df times df times m plus df times df times m times n. So the new computational cost when we use alpha would be alpha x alpha 1. So to get this, the value or the computational cost, we need to multiply the number of kernels by alpha. So here in this formula, or in this expression, what are the parameters representing the number of kernels? So we have two parameters. The first is m. So m represents the number of depth-wise convolutional kernels, and n represents the number of point-wise convolutional kernels. Since alpha reduces the number of kernels, we should multiply these parameters m and n by alpha. So we should multiply this one too. Therefore, we would get dk times dk times df times df times alpha m plus df times df times alpha m times alpha n. So this is the new computational cost if you use the width multiplier. Now, what is the reduction? So the reduction in computations is almost equal, approximately equal to alpha squared. For instance, if you use alpha equals 0.5, then the new model or the reduced model would take only 0.25, which is equivalent to 25% of computations required by the original model, by the baseline model. So this is easy to prove if you want to prove. So if you want to know how we did get such approximation, keep following with me this derivation. Otherwise, you can jump to the next. You can jump some few minutes, I think 2 or 3 minutes, to see the rest of the video. So what I'm going to do is to show how we derive this. The first thing you should do is to divide. Let me do this on another paper. So I would divide first x1 divided by x1 alpha. So I'm expecting to get this alpha squared, approximately this, right? So this x1 divided by x1 alpha is equal to dk squared times df squared times m plus df squared times n divided by dk squared times df squared times alpha m plus df squared times alpha squared times n times n. Let me just check if this is correct. df squared alpha m plus df alpha squared mn. Okay, df m. Yeah. So I should now remove some terms from this equation. So m goes out with m, n, this is n. So what goes out next is df. These terms get simplified. What else? dk. So that's all, I think. So this is equal to dk squared plus m divided by dk squared times alpha plus alpha squared n. So the next thing I want to do to simplify this, to get an approximation, so we need to have some assumptions to simplify this. But first let me factorize by, I think that I should factorize by n. So if I factorize by n, I get the following. So this should be dk divided by n plus 1, and n should be multiplied by alpha dk squared divided by n plus alpha squared, right? So now we need to have some assumptions to further simplify this. And of course our assumptions are based on the architecture, as they are not just assumptions, it's actually a truth. So n in the MobileNetV1 architecture is very high, so it ranges from something like 64 to 1024. So this is the range of n. So this n keeps increasing as we go deeper in the network. So in dk, the dk used, the size of the kernel is 3, so this means that dk squared would be 9, right? So you can see that n is higher, much higher than dk squared. What if we multiply this by alpha? So n would be much higher than alpha dk squared, because this is smaller than this. So this means that I can consider This means that I can consider that dk squared divided by n is almost 0, and also alpha dk squared divided by n would almost be 0, or very close to 0, because n is very high compared to alpha dk squared. Right? So I simplify n and n, so what I get is 1 divided by alpha squared, so this is x1 divided by x1 alpha. So that's it. So x1 alpha is equal to alpha squared x1, so this is the approximately equal to alpha squared x1. So this is the derivation if you care about it.